All right, question 7 says, suppose we divide up the year into n equally spaced periods. So example, if n were 12, then each period would be a month. You deposit $1 into a bank account that pays 100% divided by n back into your account at the end of each period. Okay, so we have our full year. We're going to divide it up into n equally spaced periods. So again, if n were say 12, that'd be 1 month per period. And at the end of each one of these periods, we're going to get a payment back into our account. And the way that's going to work is they're going to take this percentage of the previous period's balance and add that back into your account. Okay, so let's look at part A where n, the number of periods, is just 1. Okay, so in other words, the period is the full year. Okay, and what we're looking to do is find our balance at the end of the year. So our rate here, according to this rule, is going to be 100% divided by 1 in this case, which is just, of course, 100%. And so now what's our multiplier going to be? Well, if I'm going to increase this balance of $1 by 100%, I'm going to take 100% of that dollar, and then I'm going to tack on this additional amount of just, well, 100%. So in other words, it's just going to be 1 plus 1. It's going to be 2. Okay, so in other words, if I increase this dollar by 100%, I'm really just doubling it. And I'm going to get a balance at the end of the year of $2. Okay, so my dollar here will grow to $2 under this rule. Okay, now what if I divided the year up into 4 periods? Okay, these are referred to as quarters, right? Each quarter is 3 months long. And according to our rule here for our rate, we're going to take the 100% now and divide it by 4. This is 25%. So for our multiplier, we're going to take 100% of the previous quarter's balance, and then we're going to tack on 25% of that previous quarter's balance, and that's going to give us 125%, or in other words, a multiplier of 1.25. So here I'm going to multiply quarter to quarter by 1.25, and if I want to know the balance at the end of the year, well, there's 4 quarters in the year. So this number right here, this will be our year end balance. And so to compute it, what we're going to do is take our initial balance of $1, and then we're going to multiply by this 1.25 4 times. Or put another way, we're going to raise this 1.25 to the 4th power. Okay, now when you do that, you're going to get about $2.44. Okay. So I can see that by dividing the year up into 4 periods as opposed to just 1 period, my dollar is going to grow a little bit more, right? I'm going to get 44 additional cents than I got in this setup. All right, how about C? I divide the year up into 12 months. Okay, how am I going to go about finding the year-end balance now? Well, for the rate, we're going to take this 100% and divide it by 12, which is about 8.3%. It's really 8 1/3. So I'll just say, 8.333%, say, just rounding a bit. And so for our multiplier, just like we've done up here, we're going to take 100% of the previous month's balance, and then we're going to tack on this 8.333% of that previous month's balance, giving us a total of 108 and a third, right? Or as a decimal, it'd be 1.08333. So here we're going to multiply now 12 times, right? Because our year-end balance will occur here at month 12. So our year-end balance is here. And so now to compute it, really just the same kind of thing as part B, take that dollar, and now we're going to multiply by 1.08333 12 times. It's going to raise that to the 12th power. When you do that, you get about $2.61. Okay, so a little bit better than when n is 4 and when n is 1, right? So my dollar is going to grow to $2.61 about. Okay, so now what we're going to do in part D is to see what happens as we let the number of periods n get really, really large. What's going to happen to this year-end balance quantity? Okay, so we can approach this in just the same way. So for a general n, there's going to be n periods in the year. And for our rate, well, that's just going to be 100% divided by n. And 100% is just 1. So I'm going to just write this a little more succinctly. It's just 1 over n. And then for our multiplier, what we've been doing up here is saying, well, I'm going to take 100% of the previous period's balance and then tack on, right, this percent of the previous month's balance to get the new balance. Sorry, the previous period's balance, but in any event. So what am I really doing? Well, the 100% is just a 1. And then I'm tacking on this 1 over n. Okay, so this expression is our multiplier. And I'm going to apply that multiplier, well, n times, right? When n was 12, we applied this multiplier of 1.08333 12 times. Likewise here, we applied that multiplier 4 times. So here I'm going to multiply by this quantity 1 plus 1 over n times. Okay, so for the year-end balance, which would be this expression right here, I'm going to take the dollar and then multiply that by 1 plus 1 over n, 1 plus 1 over n, and raise that to the nth power, right? Okay, so now what I'd like to do is go to Desmos and plug in some different values for n and see what happens to this year-end balance as we let n get really big. Okay, so I built a table here where here's when n is 1, and I can see that my dollar has grown to $2. If n is 4, okay, then it grows to about $2.44. It's 12, then about $2.61. If, say, I broke it up by day, so 365 days for my period, grow to about $2.71. Let's say I do 1,000. You can see, right, the additional amount I'm getting by making n larger seeming to go down, right? I'm seem to cap off here. What about 10,000? Well, yeah, doesn't seem to be moving as much. Okay, yeah, definitely seem to be approaching some fixed value, right? It's about 2.71828, so on and so forth. Okay, so let's go ahead and record that over here. So what we're looking at there is a really special number, okay? This is the number E, okay? E it stands for Euler, who's a mathematician who was one of the first people to encounter this number. And so what exactly is it? Well, we're taking this expression, this 1 plus 1 over n raised to the n, and then there's that dollar out in front, but it's just $1, so I'm just going to leave it as this. And we're seeing what happens to this expression as we let n get really big. So we're looking at a limiting value of this expression, and we're seeing a value of about 2.718, and the decimals kept going there. But this number here might seem a little bit weird, but this number happens to play a really, really central role in calculus. Okay, and you're going to see this number come up in a very, very major way if you go and take calculus. But in this scenario, okay, this really is more of a finance kind of a question, and we're seeing here that if we break up the year into different number of periods, okay, each one of these payments is what's referred to as a compounding. Okay, so if I compound my account, say once versus 4 times versus 12 times, I can see the amount that my dollar will grow to is going up. But what we're showing here is that there's an upper limit to that. Okay, so if I were to compound, say 10,000 times, so 10,000 payments into my account, you might say, yeah, that's great, 10,000 payments. But notice that your rate is also going down. So there's this balancing effect, right? This number 1 plus 1 over n is just slightly over 1. And then if you raise that to a large power, okay, um, it's going to start to converge to this number that's around 2.718. All right, so that'll do it for this video, and in the next couple problems we will deal with e as the base of an exponential function. All right, see you there. Thanks.